The definition of energy is the ability to do work. All right, the ability to do work, and that's basically the longest definition you guys are going to be writing today. All right, and there's two equations that there's three we're going to focus on mainly today. The first one,
she's on her way. Sorry for interrupting you.
Oh, you're absolutely fine. Yeah, if you ever have any questions, just let me know. All right. But that's awesome to hear she's coming. All right, so gravitational potential energy. So potential energy is mass times gravity times height. So that's pretty easy. Whereas kinetic energy is equal to half the mass times velocity squared. So those are two of the three equations we're mainly going to look at today. Okay? And I kind of love this picture right here. You guys see that? Oh, I didn't mean to do that.
Does this potential energy equation apply to also energy stored in chemicals too?
Oh, you're saying that.
In chemicals?
Yes.
Potential energy. I don't know. I'm going to guess no, though. There's probably a different one. Energy stored in chemicals. I don't know. It's a great question. All right. So, do you guys see this little picture? Love it. It's hilarious. Well, what are you waiting for? Gravity.
Gravity.
Gravity. Great song. All right. So, I got this picture, or this video, and we're going to try it out. Notice how this bicyclist rarely pedals and solely relies on the gravitational potential energy to move and do his tricks. All right, so I'm going to show you a quick video, and it's going to be awesome. Okay, so we're going to try it out.
You stopped staring it.
I know.
Okay.
I got to do this. And I'm going to do one shot. Share this. Can you see my screen of this video?
Yeah.
All right, I hope you guys can hear it.
This sounds crazy, but that's probably me.
This sounds
The
awful.
audio is awful.
Okay, so it's not me.
Man.
Yep.
Okay, well, it's a cool sound. Dun, 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 dun. Dun, 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 dun. Is that better?
Very.
I could just sing it.
Much
Perfect.
better.
Dun, 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 dun. Dun, 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 dun. Anyway, stop. What's the name of that song? Stop.
I think it's
Probably in the video description.
by Buffalo Springfield or something like that.
Yeah.
Yeah.
All right. So
Forrest Gump.
basically, how's this guy able to do all these tricks without pedaling?
Gravity.
Gravity. Fantastic. Oh, he took a pedal right there. But look how awesome this course would be. Just
I'd fall within.
That sounds scary. It looks scary.
Challenge accepted.
like he literally goes on and on and on and on and on and on and on.
It's like a really great way to break a lot of bones really fast.
Yeah, that looks cool right there.
What? He just disappeared.
How did he not die?
All right. So, and then he changes bikes, which is interesting. I don't know why he does that. But what other sports require? Let me see. Let me come back to my. Oh, let's exit that. All right. What other sports require gravity? That you can utilize gravity to your potential. Ooh, skydiving.
Is that a
I
sport?
like that.
Is that a sport?
If golf
Can
is
be.
a sport, skydiving is
What
a
about soccer?
Ooh, my computer's freezing a little bit.
Are Legos considered a sport?
Like
Why
diving,
do you have gravity?
diving is just straight gravity, but I don't know if that's a sport.
Diving?
You know, like
Yeah.
swimming, but like the people that like do the tricks.
My computer's free.
I consider that a sport.
It's a
Jake,
sport.
that's an Olympic
Yeah,
sport.
Olympic
I'm pretty
and-
sure that's considered a sport.
Yeah, but like, are Olympics really sports?
Yes.
There we go.
You want to try to go to the Olympics on that?
What? Yeah, I don't know.
Then it's a sport.
I
I
know.
was out there for
Will I
like,
go to the Olympics in cheerleading? No.
No, but there's Olympics in ping pong. So
hey, there's golf
Is
Olympics.
ping pong a sport? What even is a
I
sport?
don't care what anybody says. Golf is the most boring sport to watch.
it's not a sport.
It's
True,
boring to
Dave.
watch.
No, no
But if
offense
you've
to
never
anybody
played
that
It is
plays
probably one
golf.
of the
There's a
hardest
sport.
sport end quote.
All right. Can you guys see my screen again?
Yes.
I'm
We
back.
can see it.
Man, I was gone there for a minute. Like I was just like disappeared. Just didn't want to talk to me. All right. So the law of conservation of energy. So energy. So we know matter cannot be created or destroyed. But now we know energy cannot be created or destroyed. It can only be changed from one form to another. All right. So the mechanical energy initial has to be equal to the mechanical energy of the final. Okay? So what the equation looks like is the kinetic energy of the initial plus the potential energy of the initial has to equal the kinetic energy of the final plus the potential energy of the final. Does that kind of make sense?
Mr. Bowers, can we see your puppy?
Avalanche. Come here.
Puppy, I'm at school right now.
Oh, just kidding. I lied.
But I can definitely show you a picture. Let me show you a picture real quick.
I saw the picture. I forgot you were at school for a second.
That's okay. Maybe, but I'm not going to have you guys tomorrow. Let me show you another picture.
Aww.
Say hi. Okay, I will. Back. Get back.
Okay, there's another picture of the puppy. I don't know what I'm showing you guys. I'll see
Have
the
fun.
video, so.
Hey, Emily.
But if you guys are able to see
What are you looking at?
it.
Oh, good boy.
My dog is tearing up the Christmas tree, so that's fun.
What kind of dog is that?
It's a boxer.
Oh, nice. Nice.
We have another one too. His name's Griff.
There's so many animals in this Google Meet, and I love it.
There's a nice cat.
I'm gonna go get mine. Yeah, I'm gonna go get mine. Give me a second.
Oh no, we started something.
As always.
All right. So let me get back.
My dog is present.
My dog is here now.
Wow, so many different.
Landon,
types
what kind of dog is yours?
My dog will not
Who's a
fit.
Doberman? Hey, puppy.
Aww.
My dog weighs like over 100 pounds. I can't really pick him up like that.
I can't pick her up either.
Just
I have my
believe-
toy poodle right here.
Nice. All right. So if you guys look, if you guys see all the kinetic energy and potential energy, if you add those two up on the top here, that equals 50,000, right?
Right.
That's pretty easy. But what if you add these two values right here? Once again, 50,000, 50,000, 50,000, 50,000. So all of them is going to equal 50,000. Does that part make sense?
Yeah.
Okay. So I would try to show you this video, but it only works with sound, and the sound is not working. So we're going to skip that video and go to this concept question 1. All right. So as we know, potential energy is where you're standing still. All right. So an object is sliding in a frictionless surface below. So frictionless is kind of the key word here. Starting from point B. At what 2 points does the object have the most kinetic energy?
E and D.
E and D is the exact correct answer. All right, E and D are the lowest points, so that's where it's going to have the most kinetic. Where's it going to have the most potential?
B.
B and C, right? Those are the 2 highest points. So B and C are the most potential, E and D are the most kinetic. Does that kind of make sense? Okay. All right, let's try a practice problem out. All right, during a hurricane, a large tree limb with a mass of 22 kilograms and a height of 13.3 meters falls on a roof 6 meters above ground. Dun, dun, dun. Okay. The first question says, find the kinetic energy of the limb when it reaches the roof. Okay.
How exactly is that a large limb?
I mean, 22 kilograms. So, I mean, for a limb, it's not like, I mean, I see what you're saying. But anyway, so what we're going to have to do is we're going to have to utilize this equation. Okay? We're going to have to utilize these equations. All right? So if I look at the kinetic energy equation, kinetic energy is equal to half the mass times velocity squared. Do I know what velocity is?
No, maybe.
No, I don't. Right? So I'm actually going to have to calculate the velocity first. I'm going to have to find out what the velocity is. And in order to do so, what we're going to do is we're going to use this equation to help solve it. Okay? So the kinetic energy, what's my initial kinetic energy? I'm going to draw a tree. This branch is going to fall down on the roof. Oh, that's a terrible drawing, but it's good. So this branch is going to fall down on the roof. What's its initial kinetic energy?
0.
0. I like that. So I can just get rid of that. So my potential energy is going to be the mass times gravity times height. All right. And then when it hits the roof, what's my potential energy going to turn into?
0.
That's going to be 0. So that's going to equal half the mass times velocity squared. Okay. So in this problem, what we have is the mass. Mass was 22. I forget, what's gravity?
1.8.
Hey, you guys remember. I was just checking. All right, and then the height. Okay, so the height of how far the tree fell, or the limb fell. All right, how far did the tree or limb fall?
7.3 feet.
You're exactly correct, 7.3 feet. Or, should be meters.
That's
Okay.
right.
Which is equal to half the mass. The mass was 22 times velocity squared. And from that, we should be able to calculate the velocity. All right. So I'm going to plug this in a calculator real quick. 22
I may be going off on a limb here, but I got the answer to be about 12.
That was good.
See what you did there, and I did too.
Yeah.
So the velocity is 12 meters per second. Okay? But the question asks, what is the kinetic energy? Well, we know the velocity, and we know the mass. The mass is 22. Okay, so what's the kinetic energy?
1584.
1584 is exactly correct. So that's the answer to the first question, A. The answer to the second question, what is the speed when it reaches the roof? Well, we already calculated that. The velocity was 12 meters per second. Okay, that wasn't too bad, was it? Is there any questions on
Bowers?
that problem? Yeah.
Yes. So on A, if we, like, I know we solved for velocity because that's what we needed to do for B, but for A, if, like, it was just A, couldn't you just, since we already know what, like, all the variables for the potential, the initial potential energy, couldn't you just multiply that out? And since that has to equal K, or the final kinetic energy, it would be the same thing.
Right.
All right.
Yeah.
Okay, thank you.
Yeah. I see what you did there. Yeah. Absolutely. Okay. That was a great question. Okay. So let's see. Oh, from this video. Oh man, I have another video question. I forgot. All right. We're not going to watch that video. We're going to try this out. We're going to try this problem. All right. What is the potential energy, kinetic energy, and total mechanical energy of each point? Okay. So we're going to try to calculate each point, the potential, kinetic, and mechanical.
I am so excited.
Wow, me too, actually.
This will probably end up being my last problem.
Oh, yeah, I forgot you had to leave soon.
Will there be a video recording of this?
Yeah. All right. So, let's try this out. Oh, I need a new piece of paper. Ooh, what color should I go with? I'm feeling
Purple.
green. What?
What you got?
Purple.
You say purple?
Yeah.
I'll be back. I gotta grab purple. Is pink okay?
Sure.
That works.
Okay, we're going with pink now. I'm back. I'm back. Back in the New York blues. See this nice little pink paper right here?
That looks like purple.
Hey, that's good. That's good. That was the goal, right?
Yes.
I
Okay.
just changed colors on my screen like 6 different times.
It looks white to me.
Looks purple. This goes back to the question, what is pink?
Like the projector just makes it look kind of weird.
All right.
Is it snowing where you guys are?
Yeah.
Yes.
Yeah.
It's snowing pretty hard here.
Wait,
I have to work outside later in this.
Yeah.
So what I'm going to do first is I'm going to find the potential kinetic and mechanical energy at the very top. Okay? I'm going to find it at the very top where the car is. Okay? So I'm going to have potential energy plus kinetic energy is equal to the mechanical energy. Okay? So once again, potential energy is equal to the mass times gravity times height plus the kinetic energy, which is half the mass velocity squared, is equal to mechanical energy. All right, so the mass. The mass is 10 kilograms. So I have 10 times 9.8, which is gravity, times the height. The height at that point is 100. Plus half the mass, which is 10, times the velocity squared. Now, the velocity at the very top, it tells me, is 10 meters per second. So it's going to be 10 squared. So what's my mechanical energy at the very top?
Isn't that 10,500?
10,500?
Doesn't it say it at the bottom?
Yeah, it says it at the bottom.
Well, that's just an outrage.
We can find it at like,
Did I
we're
go
supposed
too
to
fast on
find
the
it
slide?
like A, B, and C and stuff, right?
You guys weren't supposed to see that.
10,300.
10,300?
10,000.
It is 10,300.
Oh, well.
Yeah, this is what I got.
All right, so 10,000. We're gonna roll with 10,300.
Don Gray, you sound like you're on a Xbox 360 NW2 lobby.
What?
Oh my god.
Dude, I'm sorry. My mic and my like camera isn't the greatest.
No, I'm not making fun of you. That's exactly what it sounds like.
Oh, okay.
I don't see Don Gray.
Hello? My thing should be viewed, right?
All right, so I know all my mechanical energies are going to equal 10,300. So in A, what's my potential energy in A? Is it
Okay.
just going to be 0, right?
Potential. Okay.
Or my kinetic energy is going to be my 10,300.
Wait,
Wait.
and wouldn't it be the opposite because you're up so high?
No, A is at the very bottom. It's at the bottom of the first loop.
Oh, I see it. That was weird. Okay. Yep.
Yep.
Okay. Whereas B, what I have to do for B is I'm going to calculate either one, really. But so I actually have to use potential energy. I got to calculate potential because I have mass times gravity times height. So the mass is 10. Gravity is 9.8. And the height at B is 30. So what's the potential energy?
It's 2,940.
2,940. All right. How can I solve for kinetic energy?
Subtract it from
Good
10,300.
formula.
10,300 is exactly right.
We're geniuses.
You guys are geniuses. Like,
7,360.
that's what I got. Okay.
All right, Mr. Bowers, I gotta go.
No! I'm just kidding. Have a great day. We'll see you on Wednesday.
Hopefully.
Bye, Landon.
Bye, Landon.
Bye.
Bye, Landon.
Bye.
All right. Now, C. C is the same process. All right. So hopefully we're starting to get the hang of it. Letter C. Potential energy is equal to mass, gravity, height. Mass is 10. Gravity is 9.8. The height at location C is 50. All right. What's our potential energy there? Yeah.
4,900.
Okay.
Oh, I have a question.
Oh, yes, I love questions.
Is this not taking into account any energy lost from the cart into the track?
Yeah.
Because some of the energy will be transferred to the track from the cart.
Correct.
Okay.
And then to find the kinetic energy, you subtract that number from 10,300. And I got 5,400. How do you guys feel on that?
Pretty good.
Decent.
All right. So for point B, what we have to do is we have to solve for H. Okay. We have to solve for the height. All right. Now, there's different ways we can go about this. Okay. Let's see. Move over here. All right. So the velocity is given to us. So what we can do is we can solve for the kinetic energy, because kinetic energy is equal to half the mass times velocity squared. Okay. So the mass is 10. So half of 10 times the velocity, which in this case is 24.5 because that's given to us, and square that. So what's that equal?
3001.25.
3001.25. Is that what everybody's getting? That's what I got as well. So that's our kinetic energy. Now, if we subtract that from our 10,300, what's our potential energy?
Uh, 7,298.75.
Okay, so that's our potential energy. So potential energy, 7,298.75, is equal to mass times gravity times height, right? Potential energy is equal to mass times gravity times height. Well, I know mass is 10, gravity is 9.8. What is H? And that's the goal. What is H here? And only one. So 1 6 would be 70. Does that kind of make sense? Is there any questions on that one? All right. Question. Shaun White snowboards down the super pipe. Have you guys ever seen Shaun White?
Isn't he on TikTok?
I'm looking it up.
I used to have a Wii game called Shaun White Snowboarding, but I never opened it, so I couldn't tell you.
So note that his height from the ground is tracked from the top left corner. So there's a video of him going down. I wish I could show it. Maybe I can. No, that's Tony Hawk. No, that's pretty cool too. The Loop of Death. Have you guys ever seen that video?
He is
No,
on
but that
TikTok.
was scary. I told you. Ooh.
Yeah, he is on TikTok.
Oh, that's cool.
3-time Olympic gold
Cringe
medalist.
noises.
In the half pipe, so he's or super pipe, so he's really good. So explain why each jump after his first jump reaches a lower height than the jump before.
More kinetic or more potential energy.
Less
No?
potential energy.
So, well, really, the answer is friction of the ground. So the friction of the ground is causing less kinetic energy at the bottom, and result, less potential energy at the top, right? Some of the kinetic energy is transferring to friction. All right. All right. This is going to be our last example for today. And then we'll go have a little bit of practice. All right. So a frictionless roller coaster with an initial speed of 10 meters per second at an initial height of 100 meters has a mass of 1,000 kilograms. Wow. What is the speed at point A? What is the speed at point A is the first question. What is the speed at point B? And how high will it move on the last hill? Okay. So there's a lot of things to consider here. Okay. So let's see. What is the speed at point A? Well, point A is the same height as the start. So it's going to be the same speed, right? Since it's frictionless, it's going to have the same speed. So the initial speed was 10 meters per second. So at point A, the speed is just going to be 10 meters per second. Does that make sense since it's the same height? Okay. So what is the speed at point B? Okay, this is a little different. Okay. What is the speed at point B? All right. So here, I got to do my mechanical energy initial equals mechanical energy final. So KE initial plus PE initial potential energy is equal to my kinetic energy final plus potential energy final. Let me zoom in. Okay. So kinetic energy final. So it's going to be half the mass. So half the mass. So the mass in this case is 1,000 times velocity squared, which at the initial, my velocity was 10 meters per second, right? Plus the potential energy, so mass times gravity times height. So my height at the initial was 100 meters. Does that make sense so far? So that's going to equal my kinetic energy final. So kinetic energy, so half the mass. Oh, I'm running out of space. I'm going to zoom out a little bit. Half the mass times velocities squared. Now, in this case, do I know the velocity? No, that's what I'm solving for. So velocity squared plus mass times gravity times height. So mass times gravity times the height. So height, my initial height was 100. Here I know it's half of that, right? So if you look on the PowerPoint, half of 100 would be 50. There's a lot of numbers on that. Holy smokes. So you got to solve for V. Okay, you got to solve for the velocity. All right. So you got to plug it in your calculator. All right. I'm going to do it slowly but surely.
Mr. Bowers,
Yes.
are your nails painted or is that just the light?
It's just the light. Do you see my name?
Okay. Yeah, it looks like they're painted.
Fascinating. What color do they look painted?
They just look straight white to me.
Green.
Yeah, I got green on the camera.
Okay. All right.
I do. Okay. Plus 1,000 times. All right, so I got an answer of 32.9. Is that what you guys are getting? Maybe so. Is there any questions on how to solve for B? Okay, and then C says, how far will it move up the last hill? How high will it move up the last hill? Okay, so on this type of problem, what you're actually going to do is you're going to have the same start. All of this is going to be the exact same. Okay, so what I'm going to do is I'm just going to get a different piece of paper. I'm going to put it right there. So what that's going to equal is my kinetic energy final plus potential energy final. Okay, what's my kinetic energy final going to be at the very top of the hill over there? My kinetic energy.
0.
It's going to be 0. So I'm going to see how far I can go up, and then it's going to stop. So that's just going to be 0. So my potential energy on the right side is going to be what I'm going to be solving for, right? So the potential energy is mass times gravity times height. Okay, so I know the mass. The mass, once again, is 1,000 times gravity, which is 9.8, times h. Okay, so what you're going to do is you're going to set all of this equal to 1,000 times 9.8 times h, and you got to solve for h.
With stick fix, I got about 110 meters.
Wow, you did that very fast. What did you get?
I got about yeah.
Interesting. I got about 15.
Oof.
Let me try it again.
Where's the 0, man?
I did it quick because I already like solved the left side equation
Right.
from the last problem, and then I just did.
Oh, I got 105 this time. Is that close to what you got?
Yeah, and then I did stick fix.
Yeah. So in this, there's going to be 1 sig fig, so 100.
Oh yeah, you're right.
All right. Man. Can I stop sharing? Everybody got that copy down? Is everybody good? Okay. So that's a little introduction to mechanical and potential energy. Okay. What we're going to be looking at coming up is some springs, how springs conserve energy. And then we're going to look at, then we're going to do a lab. We're probably going to do an experiment on this on, well, not Wednesday, Thursday then. Okay. We're going to do an experiment. It's probably going to be a 2-day experiment. So Thursday and Friday, we'll analyze these different numbers of potential kinetic and mechanical energy. All right. But is there any questions based off of today? All right. If you guys can apply those 2 equations, and actually, I'm 90% sure. For some reason,
Are you looking at the equation sheet?
I'm looking. I thought they were.
They are on you there. They are on there.
And I think kinetic. Yep.
Kinetic is on the left side, and then the potential one, I believe, is like directly underneath all the letters. It uses a U. Like all the.
Mr.
Oh.
Bowers, I have a question.
Yeah, absolutely.
So are we gonna be using the sheet that we already got on like the exams and stuff, or will they give us a new one?
That is why I literally gave you this. I was tempted to create an equation sheet for each chapter. That's what some teachers do. I thought it was a good idea to just have this because this is what you will be given on the AP exam.
Okay.
So
also, sorry. Go ahead.
You're good.
So like in class, some of the equations that we use that aren't on that sheet, I wrote down. Am I still like allowed to use that in class? Like I wrote down the mu and then the mu equation and then the, yeah.
That's on here.
Oh, it is?
Yeah. All the equations we use have been in here so far. They're just in.
I think I just wrote it next to it, like in a different version or the way that I like could recognize it. So then.
Yeah, that's fine.
Okay.
Yeah. So yeah. Any other questions? We feel pretty good.
It's snowing outside.
That's some good news. I'd rather snow than
Snowing.
Pretty epic.
I said, what if we have like a snow day?
That'd be awesome.
What do they even did they ever figure out what we're gonna do for snow days? Like if we're actually gonna have a day off or we just do this online thing again?
That's what I'm doing right now.
I didn't hear
pretty
you.
bummed on it. I kind of like my snow days.
Yeah.
Yeah.
But I can see the school being like, well, I mean, you guys can go online, so
They probably will make us
Yeah,
go
probably
online
do.
so we don't miss any more school days than we already have.
But like, is anybody gonna show up? Like, let's be honest, I'm not showing up.
I mean,
Cole coming in clutch. All right. So what I want you guys to do, we still have about 20 minutes. All right. I did post a little activity on Google Classroom, but I only want you guys to do the very, very first part of it. Okay. So I'm going to show you what it looks like here real fast. I only want you guys to do the very first part. And it's easiest to do using Cami. So if you look, that's what it's called. Energy and work. All right. If you look at this, I just want you to do question number 1. Okay. Question number 1. All you got to do is answer circle increase, decrease, or equal to. All right. Does that kind of make sense? So a marble begins at an elevated position on top of an inclined ruler and rolls down to the bottom. All right. In this example, does the kinetic energy increase or decrease?
Increase.
It increases. What happens to the potential energy?
It decreases.
All right, so if the kinetic increased and the potential decreased, that means the mechanical is going to be the same. Does that kind of make sense? All right, so what you can do is you can circle these on Cami and just try your best. All right.
Mr. Bowers, what do we put for like time and stuff? I don't really understand that.
The TME, that's a great question.
It's cool.
Oh,
is
okay.
full mechanical energy.
Oh, okay.
That's always just equal, right?
Not quite. So if you actually read the second one, a marble is rolling along a level table. When it hits a note card, it slides to a stop.
Okay.
So if it slides to a stop, what happens to your kinetic energy?
It
Your
goes
kinetic
down.
energy will go
It
down.
decreases.
You'll lose energy.
Right? However, a marble rolling along a level table, the potential energy will actually stay the same. The potential energy doesn't change because it's mass times gravity times height. So the mass didn't change, gravity didn't change, and did the height change? No, so the potential energy is equal to, okay? So if the kinetic goes down and the potential is equal to, that means the mechanical also went down. Does that kind of make sense?
Yeah.
All right, so you just got to kind of check that out. Tommy, that looks delicious.
What is that?
Man, I am so jealous.
Tommy,
It's,
what is that?
I
It's
can't see
a
it.
full baguette from Panera.
Oh, man.
You good, Brady?
Brady got that energy. I like it.
Sorry.
That's what I'm talking
Sorry, don't
about.
want to make people hungry.
No, it's fine. I'm just over here. I had chicken noodle soup.
I'm hyped for the baguette. Let's go.
So, all right.
Thanks, Brady.
Is there any questions about what you guys are doing? Just answer A through G. You guys are done.
Do you want us to turn it in when we're done?
Yeah, actually. Yeah.
Just A through G?
A through G. That's it.
Okay, so on question 9, and how do we actually find the maximum compression?
You have question 9 on the back or on the second page? Yeah. All right. So let's see. Assuming the initial, when it hits the ground of the base of the cliff. Let's see. Is my question 9 different than your question 9? Oh, my question 9 is different. A block. Okay. How fast? What is the maximum compression? Oh, all right. So we haven't got that far. But what you're going to have to do is find the kinetic energy of the initial, and that's going to equal the potential energy of the final. But you're going to have to solve for the the compression. So you're actually going to have to solve for an X value. Okay. We haven't got that far, but do you actually want me to show you? You're muted.
Sure.
Okay. Now, the rest of you, if you guys have any questions, let me know. If not, you guys can log off at any time. I hope you guys enjoy the rest of your day. And we'll see you guys on Wednesday.
I have a question.
All right, see you, Mr. Bowers. Thank you.
See
I have
ya.
a question for Brady.
Question for Brady.
Yeah. Do you know what we're doing for engineering? Like,
It
do
looked
we even
like-
have a meet?
Look like Brady
Or
just
is there-
logged off.
I think it's just gone. All right.
Man. Okay. So what I'm going to do is I'm going to present how to solve number 9. Here we go. Let's go back to this. All right, it's actually pretty easy. Okay. So let's see. How fast is the block going when it has compressed the spring of 0.05 meters? Okay. So to start this problem, what you're going to have, you have to solve A first before solving B, right? So the
Yeah.
mechanical energy initial is equal to the mechanical energy final. Okay. Now, how fast is the block going? So when we're solving this, you're going to have the kinetic energy initial plus the potential energy initial is equal to the kinetic energy final plus the potential energy final. So the initial, it's moving at a speed of 4 meters per second on a frictionless surface toward a spring. So there is no potential energy at the initial. So that's going to be 0. All right. And then the final, we're going to have both. Okay. So the initial kinetic energy. So we're going to have half the mass. The mass is 2 kilograms times the velocity squared, which is 4 squared, is equal to the kinetic energy final. So let's see, where am I? All right, and this is where we involve the spring constant. So what instead let me get this right. Two kilograms, the spring constant is 200. So this is where we have, it's actually going to be the kinetic energy, it's going to be half the mass times the velocity squared, which we don't know. We're actually solving velocity. But the potential energy, this is where we have to calculate or analyze the compression. Okay? So the compression is actually going to be half the mass, half the spring constant. So this is going to be half the spring constant and then that's going to actually be multiplied by the compressed squared. Okay?
Is that the force?
Yeah, I mean, yeah, theoretically.
So compressed squared would be just 1 squared?
Well, in this, the spring constant in the problem is given to be 200.
It's 20 for mine.
What?
Is that one different too?
Oh, mine says 200. Oh, I see yours. Yeah, yours says 20. My paper says 200. Fascinating. We'll go with yours. So 20 times the spring constant. The spring constant in yours is 0.05. And square that. Okay, so you have to solve for V out of all of this. So let's do that. I got about 4.
Yeah, that's what I got too.
Okay. So I got, how fast is the block going? So I got the velocity to be 4. Okay. So in part B, what you're actually going to have to do, so you have your mechanical, what is the maximum compression caused by the block? So the compression, once again, you're going to have the mechanical energy initial. Mechanical energy initial is equal to the mechanical energy final, where once again, the potential, that's not a factor right now. So we're going to have half the mass times the velocity squared.
But for the maximum, when fully compressed, would the velocity be 0? So it would just be equal to the potential energy final.
Yes, so this is going to be equal to the, correct. So kinetic energy final plus potential energy final. The kinetic is going to be 0, so we're not going to take that into factor. So this is going to equal the potential energy final, all right? But it's going to be with the spring constant up here. So this is what we're going to be using. So it's
it'd
going
be
to be half the spring constant. So your spring constant was 20.
Yeah.
Times the compressed. So we're going to use X because we're trying to see the maximum amount of compression squared. And you just got to solve for X.
So I got 1.26 for X.
I got 1.26 as well.
All right.
And that's how you analyze the compression. And theoretically, that would be X's displacement, so meters.
Okay.
We haven't got that far, but that's how you'd solve it.
All right. Thank you.
Does that kind of make sense?
Yeah.
Which I'm pretty sure that equation is also on your formula sheet. Let me see if I can find it. Yep. So that's U is equal to 1/2 kx squared. K is the spring constant, x squared is the compressed displacement.
Ah.
It's the second from the bottom, if you can see it.
Okay, so it's just under the force from spring?
Yep.
One?
Yep.
Okay. Thank you. All right.
Any other questions?
Nope.
Very good. All right. Well, I look forward to seeing you on Wednesday.
Bye.
See ya.